In this video, we are going to discuss the color of lanthanide ions. Lanthanide ions have a characteristic color and which is independent of nature of ligand or nature of group which is attached to metal ion, lanthanide ion, to form the compound. And the color of lanthanide ion, it is due to presence of unpaired electrons. It may be due to presence of unpaired electrons, but the presence of unpaired electron, it is not the only condition to have a color of lanthanide ions. Now look at this table. These are the lanthanide ions in +3 oxidation state. Out of various lanthanide ions, lanthanum +3, lutetium +3, unpaired electrons are absent or not present in case of these two elements, and unpaired electrons are 0. These ions are colorless. Cerium +3 and ytterbium +3, these two ions respectively contain 1 unpaired electron each, even though these are colorless. And gadolinium +3, it contains 7 unpaired electrons, even though it is colorless. Whereas other lanthanide ions like praseodymium +3, neodymium +3, samarium +3, promethium +3, samarium +3, and europium +3, these ions contain unpaired electrons like 2, 3, 4, 5, 6 respectively, and they have a color like green, reddish, pink or yellow, pale pink, etc. Similarly, thulium, ytterbium, erbium, holmium, dysprosium, terbium, these ions also contain unpaired electrons, and these ions are colored like green. Thulium is green, whereas terbium +3, it is pale pink. So lanthanum +3 ions with X number of 4f electrons have a nearly same color as the ion having 14 - X number of f electrons. Now consider the example of promethium +3 and holmium +3. In promethium +3, f orbital contains 4 electrons, that is X is equal to 4, and it has a pink color. Whereas holmium +3, in 4f orbital there are 10 electrons, that is, as value of X is 4, 14 - X becomes 10. So its color must be same as promethium +3, and it also has a pink color. So promethium +3 contain 4f electrons, its color is pink. Similarly, holmium +3 contain 10 f electrons, that is, as per 14 - X, number of electrons should be 10, and because of holmium and promethium, they have a same color. It is applicable to other ions also. So as such, there is no any correlation between number of unpaired electrons and color of ion. Hence, isoelectronic ions have different colors like lanthanum +3 and cerium +3. In these ions, there is no any unpaired electron, but lanthanum +3 is colorless, whereas cerium +4, it is orange colored. Europium +3 contains 6 unpaired electrons, samarium +2 contains 6 unpaired electrons. So europium +3 is a pale pink, whereas samarium +2 is reddish. Similarly, gadolinium +3 and europium +2 contains 7 unpaired electrons. Gadolinium is colorless, and europium +2, it has a straw yellow color. Lutetium +3 and ytterbium +2 contain 0 unpaired electrons. Lutetium +3 is colorless, whereas ytterbium +2, it is a green. Now next point is absorption spectra of lanthanides. Most of the lanthanide ions are characterized by well-defined, sharp absorption spectra. When we compare absorption spectra of lanthanides with the absorption spectra of 3D elements, in case of 3D elements, absorption spectra has a broad peaks or broad bands, but here lanthanide ions shows sharp absorption spectra. For example, praseodymium chloride, this is the absorption spectra of praseodymium chloride. There are sharp peaks. Even neodymium chloride, this is the absorption spectra of neodymium chloride, it has a sharp peaks. Now this absorption spectra, it results due to FF transition of electrons, that is the transition of electron from one f orbital to other f orbital. Some energy is associated with these transitions, and because of absorption of part of electromagnetic radiation, there is a absorption spectrum. So this absorption spectra of lanthanide ions, it is not affected by the complexing ligands. It is independent of which ligand is attached to particular ion. Okay, whether complexing ligand like ethylene diamine or citric acid or ethylene diamine tetraacetic acid or monodentate ligand, which ligand is attached, it is not a spectrum or position and intensity of this absorption spectra, it is not affected by nature of ligands. And because of this, the absorption spectrum of lanthanide, it is used for qualitative and quantitative estimation of lanthanide ions. Now next point is ability of lanthanides to form the complexes. Lanthanum plus 3 ions have low charge to radius ratio, hence they show the poor tendency towards complex formation. Lanthanides form limited number of stable complexes, and because of shielding of 4f electrons by 5s and 5p orbitals, there is a weak interaction of 4f electrons with electric field produced by ligand, and because of this there is a less crystal field stabilization energy. This makes the complexes of lanthanide ions less stable. However, lanthanide plus 3 ions, these are typically class A acceptors, and hence these ions can form more stable complexes with ligands having more electronegative atoms like oxygen and fluorine. So basically they have less tendency to form complexes, but these ions can form comparatively more stable complexes with the ligands having oxygen and fluorine as donor elements, because these are more electronegative atoms. The complexes with chelating ligands like ethylene diamine tetraacetic acid, citric acid, oxalic acid, acetyl acetone, these are fairly stable, whereas the complexes with ethylene diamine, which contain nitrogen as a donor, are less stable, and such a complexes are easily hydrolyzed. The examples of known complexes of lanthanide ions are ion pair associations like LnF2+, LnSO4+, LnC2O4, this is oxalate, lanthanide oxalate, plus then adducts of ammonia, LnI3, XNH3, then chelated non-ionic complexes like LnAA3, XH2O, where A, it is a bidentate ligand, and this is the chelated non-ionic complex of lanthanide ion. Chelated ionic complexes like LnEDTA, EDTA, it is a ethylene diamine tetraacetic acid, ln EDTA minus ln C6H5O7 twice 3 minus. So C6H5O7, it is a citric acid. So these are the chelated ionic complexes. The chelates with more number of rings are more stable. And the chelates or chelating complexes have high stability constants, and these stability constants increases with increase in size of lanthanide ions. This makes easy separation of lanthanides by ion exchange method. Actually, the complex formation ability of lanthanide ions with some of the chelating ligands, it is useful for separation of lanthanides. You know, lanthanides have almost similar chemical properties. Their oxidation state is similar, size is almost same, but actually there is a small decrease in size from lanthanum plus 3 to lutetium plus 3, and because of this small decrease in size, gradual decrease in size from lanthanum to lutetium, their ability to form complex with the chelate ligands, it changes, and because of this different ability, the stability of these complexes are also different, and the stability of complex increases with decrease in size, and therefore stability of complex increases from lanthanum to lutetium, and this makes easy separation of lanthanides by ion exchange method. Other examples of the complexes of lanthanides are the nonahydrated or nonaquo neodymium plus 3, its coordination number is 9. Lanthanum acac 3, this is acetyl acetonato 3, this is the chelating ligands H2O2. So this is also complex with chelating ligands, its coordination number is 8. Now summary of this point is, lanthanide ions, they displays different colors, and color of lanthanide ions, it may be due to unpaired electron, but unpaired electron, it is not the only condition to have a color of lanthanide ions. Lanthanum plus 3, lutetium plus 3 and gadolinium plus 3, these are the colored ions. Colorless ions. Lanthanum plus 3, lutetium plus 3 and gadolinium plus 3, these are the colorless ions. Now lanthanide ions shows sharp absorption spectra, which is useful for qualitative and quantitative estimation of lanthanides, and lanthanide ions have less tendency to form complexes, and especially they form fairly stable complexes with chelating ligands, and more the number of rings, more is the stability of chelates. Okay, so these are the some highlighting points about this video.